So we have the disk, in its center the bulge, and around this we have a halo. The halo contains about 150 global clusters with typical masses of up to about 1 million solar masses, and it turns out lots of field stars. So there are population 2 stars orbiting in high inclination orbits that are not part of globular clusters. In fact, we now know that 99% of the mass of the stars in the halo is outside the globular clusters. Globular clusters are a very visible minority. Furthermore, about half of all of these, 40%, orbit with inclinations larger than 90 degrees, which makes them retrograde orbits. So if the stars in the disk are orbiting one way, these stars are orbiting by and large in the other direction. So the angular momentum of the halo in net is about 0. In terms of size, remember Shapley had a large halo of 100 kiloparsecs, taking into account absorption and correct distance measurements. All but about less than 10 of the globular clusters and most of the field stars are within 50 kiloparsecs. So typically one says that the halo is a sphere of radius 50 kiloparsecs. Notice this is twice the size of the radius of the disk, so the halo is larger and envelops everything. Of course, some of these objects are in the disk. We detected them first as population 2 stars in the solar neighborhood that just happen to be moving with the wrong velocity. And all of the stars in the halo, as we said, are old, between 11 and 13 billion years. What else is out there? Well, we knew that the halo was permeated by warm gas. We could observe that because warm gas, by warm I mean up to 100,000 or a few 100,000 Kelvin, absorbs visible light, and so we could see the visible light absorption from the halo. Some of the hydrogen atoms are excited, some of the other atoms are there and have lower excitation energy than hydrogen, so we could track the gas in the halo, and there's not that much, it's not a significant mass. A new discovery from September this year, so I'm putting it in there with an asterisk because I don't know how verified it's going to be, is that there is another gas component in the halo. This is hot gas with temperature of 1,000,000 Kelvin, which makes it transparent to visible light because there are no electrons with that excitation energy, but it has been observed through X-ray absorption by oxygen, highly ionized oxygen atoms in this gas, and if the Chandra result holds, then this halo might extend as far as 100 kiloparsecs, so that's more than 300,000 light years, and that's past, to give you a sense, the Large Magellanic Clouds, and may contain as much mass as the entire stellar population of the thin disk, so 60 billion solar masses. Again, over again, the mass of the thin disk might have been lost until recently in the form of this halo of hot gas. Note that this is twice the radius of the globular cluster halo. So we're beginning to construct our model. I mentioned the Large Magellanic Cloud, and indeed the Milky Way is not alone. There are satellite galaxies, a few dwarf satellites, as well as the Magellanic Clouds orbit the Milky Way. I should point out that there are, it's not quite clear whether the Magellanic Clouds have a positive, or just negative kinetic, total energy relative to the Milky Way. In other words, are they in bound orbits, or are they moving off and at some point will disappear, but not in my lifetime. In any event, they are certainly currently very near the Milky Way, and we can see, as we'll talk about the evidence of their tidal interactions with the Milky Way, some other galaxies some other of these dwarf galaxies are currently in the process of being ripped apart by the tidal forces of the Milky Way, which are breaking them up into rings. The objects in the ring are being slowed down, and eventually these dwarfs are merging to some extent with the Milky Way gobbling up dwarfs and growing. This, we'll see, is part of the processes of galactic dynamics, so it pays to at least enjoy a look at two of our neighbors. To the left, obviously, the spectacularly beautiful Magellanic Clouds. If you've never seen them and have a way to get to the southern hemisphere, by all means do. It's a mind-blowing experience. I've done it once and I can't forget it. To the right, the Leo 1 dwarf. This is what a dwarf galaxy looks like. Of course, this is a long exposure picture. You probably would completely miss it and look right through it. The way that we identify these objects as being part of separate galaxy is by tracking both their chemistry, their metallicity, and their proper motion. And radial motion, we see a group of stars in a given direction that all seem to be moving in concert. Then we can study their random motion and see that they are in fact gravitationally bound to each other. And then if the group is large enough, dignifies them not as a star cluster, but as a small galaxy.